Hello, everybody. So first of all, I would like to thank the organizer to let me present this work today at TAUP conference based on a work that we have submitted on arXiv last month. And in particular, today I'm going to discuss the possible direct detection of light dark matter particle from evaporating primordial black hole. The topic of this talk is the direct detection experiment for the matter particle. So this experiment aims at uncovering the matter properties by measuring the nuclear recoil energies released in the detector after the interaction between nuclei and the matter particle that surround us. So this plot here is showing the current status of direct detection experiment. In particular, given the no evidence so far for the matter particle, all these experiments here have been able to place very strong constraints on the dark matter nuclear spin-independent cross-section as function of the dark matter mass. So these experiments are very powerful to look for the matter particle with a mass larger than 1 GeV, but the constraint become much weaker for lighter sub-GeV dark matter particle because the recoil energy released to the detector becomes very small. And so sub-GeV dark matter particle with a mass smaller than 1 GeV are almost undetectable with direct detection experiment. So the possible way out for allowing us to probe light dark matter particle is, for example, to consider light nuclei, argon instead of xenon to reduce the mass of the target nuclei, or to consider additional effects occurring in the detector, for example, the Migdal effect. Or in general, these experimental limitations can be circumvented in scenario of boosted dark matter particle. In this case, a sub-component of the matter particle has a much higher velocity, reaching the velocity of light, and this basically increases the recoil and the nuclear recoil energies released in the detector, which is nothing else than proportional to the transfer momentum between nuclei and dark matter. So today I'm going to present a new mechanism for to produce boosted dark matter at present times, and in particular, this is based on the evaporation of primordial black holes. So primordial black holes can have been produced after inflation due to density fluctuation, and so they possibly exist in our galaxies and in the whole universe. So light, the primordial black hole, can evaporate in all the particle decay freedom of standard models, and in particular, if the matter particles are light enough, they can also be produced in the evaporation of primordial black holes. And typically, these dark matter particles have very high kinetic energies, so they are relativistic dark matter particle. So this particle, so this the primordial black hole can produce a flux of boosted dark matter particle that can reach us or reach the detector after propagating through the atmosphere and the Earth. And this detection can allow us to place very powerful some constraint on the joint parameter space of primordial black hole and dark matter. And we refer to this scenario here as EPBH dark matter. So the evaporation of primordial black hole into dark matter particle has already been studied in the literature, but only has a way to produce dark matter in the early universe. So here instead we consider the production of boosted dark matter in the present universe. So let me also highlight or suggest to look at the talk by Roberta Calabrese at the TAUP conference that will discuss the production of active neutrinos from the evaporation of primordial black hole. In this talk, I'm going to discuss the production of boosted light dark matter from the evaporation of primordial black hole, then the propagation of these dark matter particles to the atmosphere and the Earth, and then the detection in a direct detection experiment, such as a xenon 1-ton detector. So as a result of general relativity and quantum field theory, Hawking demonstrated that light black hole, and in particular primordial black hole, can evaporate in light particle degree of freedom. And this radiation is a thermal gray body spectrum with a temperature given by this expression, so inversely proportional to the pph mass. So all the particles lighter than the Hawking temperature here can be efficiently produced by the evaporation of primordial black hole, and the same can happen for light dark matter particle. So here on the left, you can see the gray body spectrum for a dark matter particle of 1 MeV for 3 different pph mass. So you can see that the peak of this distribution, which is basically defined by the Hawking temperature, is different for different pph mass. So this spectrum here, we compute using the public available code Black-Hawk. We consider the conservative scenarios with spinless and chargeless PBH. In different cases, the PBH evaporation rate is faster, and so the production of dark matter particle is also more efficient. And then we consider a fermionic degree of dark matter particle with 4 particle degree of freedom. So you can see in this specific case, the evaporation of primordial black hole is able to produce dark matter with very high kinetic energies, and so these dark matter particles here are relativistic. The abundance of PBH is strongly constrained by several cosmological and astrophysical measurements, and also through the mechanism of the evaporation into a standard model particle, like, for example, in gamma rays, charged particle, and so on. So the abundance of PBH, defined as this parameter here, half PBH, for masses of 10 to 15 grams should be much, much smaller than 1, which also means that in this mass range, primordial black hole cannot count for dark matter in the universe. There are also active searches for looking for the possible burst into neutrinos and gamma rays from the final stage of the evaporation of primordial black holes, and I refer to this paper here to these kind of searches. So after we have once we have the energy spectrum from a single, from the evaporation of a single primordial black hole, then we computed the total flux of the matter particle produced by the galactic and extragalactic population of primordial black hole. So the galactic component of this flux, here shown with the solid line, follows the dark matter distribution of our galaxy, for which we consider the standard Navarro-Franke-White profile. And as for all as for standard indirect dark matter searches, the galactic component has a strong dependence on the angular galactic coordinates and peaks towards the galactic center. The extragalactic component instead, shown here with the dashed line, follows the cosmological dark matter distribution and needs and also has a redshift dependence. Different from the galactic component, this extragalactic one is isotropic, so does not depend on angular coordinates. So this flux here is proportional basically to the density, to the fraction or the abundance of PBH, for which we consider the maximum allowed value. And for this specific case of 10 to 15 GeV, the maximum allowed value for FPBH is at the level 10 to minus 7 according to present constraint, and then it's proportional to the dark matter density. So these flux of dark matter particle, which again are relativistics given the high kinetic energies shown in this plot, also depends on the PBH mass, as you can see here in this plot on the left, and in particular for larger PBH mass, for example, for 10 to 15 grams in light blue. In this case, we have a smaller Hawking temperature, which means that the matter particles are produced at much smaller kinetic energies. They have a slower evaporation rate, this suppresses the flux, but on the other hand, heavier PBH are affected by much weaker constraint on their abundance. So this is why the flux at the end is the highest. On the other hand, for smaller PBH mass, like 5 times to 10 to 14 grams, they have a larger temperature, reaching producing the matter particle at higher kinetic energies, faster evaporation rate, but on the other hand, they are affected by strong constraint on FPBH. So given this behavior here, in this work, we focus only on this mass window for the PBH, because it's the one that we found a detectable signal in a direct detection experiment such as xenon one-ton detector. So after computing this flux of dark matter particle from the evaporation of primordial black hole, we need to account for the propagation of the matter particle through the atmosphere and the Earth before reaching the detector. Indeed, the same interaction occurring in the detector also occurs with nuclei in the atmosphere and the Earth, and this causes energy loss. So we follow this reference here. In particular, we adopt an analytical approach based on the ballistic trajectory approximation. So in this framework, the interaction length becomes comparable to the Earth diameter at around 10 to minus 31 centimeters square for the spin-independent dark matter nuclear cross-section. And for values larger than this, propagation effects are very important. However, let me stress that we have also a diffuse extragalactic component of the matter particle from the evaporation of extragalactic primordial black hole. In this case, half of the flux will reach the detector only after traveling mainly the atmosphere. So this is also, the atmosphere is also a region where the energy loss of the matter particle is much lower. So after propagation, we compute the differential rate of event in the xenon one-ton detector as function of the recoil energies of the xenon target nuclei. And we consider an exposure of 1 ton here and adopt this expression where we consider a flat distribution for the maximum and low recoil energies. So in this plot, you see the ratio between the differential event rate divided by the dark matter cross section, and you can see that for small enough dark matter nuclear cross section, this ratio is basically independent from the cross section, because the differential rate is nothing else than proportional to the abundance of PBH times the interaction strength between dark matter and nuclei. And actually, there is a strong degeneracy between these two parameters here. On the other hand, for large cross-section, propagation effects are very important, and they basically, the propagation basically push the events in the detector to much lower recoil energies, because the energy loss during the propagation are much more important. So we consider the latest xenon one-ton result that has observed no excess of events in this energy range. And then we recast their limits on GV dark matter particle to light dark matter particle produced in the EPBH dark matter scenarios. And then we get these constraints for the spin-independent dark matter cross-section as function of dark matter mass. So as you can see here, we found a significant improvement with respect to previous constraint, shown here by the gray area. And actually, we are able to improve by up to 4 orders of magnitude in cross-section, and stronger constraints occur in the case of a PBH population with a mass of 10 to 15 grams. Let me also stress that these constraints here apply even to lighter masses, so they extend to dark matter masses lighter than 1 keV, but in this mass range, for fermionic direct dark matter particle, there exists very strongly constraint. So this is why we show this constraint only up to 1 keV. This is for the parameter space of dark matter, but we also have constraints on the parameter space of primordial black hole. So the abundance of primordial black hole is function of the PBH mass. So these constraints here are valid in any model of a light dark matter particle, and in particular, they depend on the cross-section between dark matter and nuclei. So they linearly depend on the cross-section, as you can see here, for small enough value for the cross-section, while for cross-section larger than 10 to minus 31, we have the propagation effect become important, as I said before, and so this caused this very peculiar behavior for the red Sollenheim. But in any case, you can see that in the EPBH diameter scenarios, we are able to improve the current constraint on the FPBH by a few order of magnitudes, depending on the diameter cross-section. So let me conclude. We have pointed out that evaporating primordial black hole with a mass from 10 to 14 to 10 to 16 grams are a very efficient source of boosted light diameter particles today in the present universe. And for the first time, we have explored the phenomenological implication of the EPBH diameter scenario in direct diffraction experiments such as xenon 1 ton. So focusing on xenon 1 ton, we have placed a strong and very powerful constraint on the combined parameter space of dark matter and primordial black hole. And stay tuned, because this scenario has a very rich phenomenology to be explored. Thanks for listening.